Okay, so you now know that we have two important integer parameters. The first one is k, which is the number of hash functions in just one table. The second important parameter is the L, which is the number of tables or partitions. So geometrically, we call them, in machine learning, we call them landmarks. For example, you have some data sets, and for example, like this, and you have some landmarks in red. So these points are, for example, let's say, the images of some people. And you want to see that, for example, each landmarks provides a hash. So it is hash 1, this is hash 2. I have shown you that in INRIA, for example, they use the inner product of those Gaussians with the points in compressive machine learning. And now we are doing it exactly the same way, but in the language of nearest neighbor search. So in each of L tables, we sample k hash functions, h1 through hk. So you may ask, what is the hash of P? It is h1 of P, h2 of P, and hk of P. And now to answer a query Q, we iterate over all L tables, and in each table we retrieve the data points that hash to the same bucket as Q. So it means that, for example, yes, I got it. This is the hash of Q is the same, and the bucket is this, 3, 2, 5. This is the bucket. I got it. So as soon as we find a point and say, I got it, with distance CR from the query, we stop immediately. And you may ask, but how to set K and L, these important parameters? We choose K to be the smallest integer such that P to the K is at most 1 over n. Then for a fixed query and a given table, there will be at most n P to the K, which is less than 1, 4 points that fall into the same bucket with the query. So now we can find the expected query time, which is n to the constant number and L. So it remains to choose L because I have defined K, how to choose K like that. Now for choosing L, I say that the probability of success of a single table is at least P1 to the K. And we have chosen K to be log n over log of 1 over P2. And this is greater than n to the minus rho P1. Because this is P1 n to the rho, and thus to get a high probability of success, we can just choose L to be order of n to the row divided by P1. And now let's talk about the spherical symmetry, this important property. So we have a Gaussian distribution n with mean a and variance sigma 2. So just to remind you that f of x is this. So we have fixed orthogonal matrix. If you multiply this matrix with a d-dimensional vector of normals, don't forget that this is just normal again. This property is very interesting. And spherical symmetry implies two stability. It means that if V is distributed according to d-dimensional normal variable, and also U is in Rd is an arbitrary vector, then U and V is distributed according to normal of 0 and U2. So you have seen I have used this several times. So now U and V is just a U and a V, and A is a fixed orthogonal matrix. So Ilya Razenshteyn separates two problems. Say, for example, I want to find nearest neighbor search for a data-independent partition. And another category is that he wants to find data-dependent partitions. So for data-independent partitions that he uses in his PhD thesis, we take P to be inside. We sample T IID Gaussian d-dimensional vectors Z1, Z2, and ZT, all of them in Rd, and Pi is in P, and Pi is all your points that have the inner product with those, I say landmarks, I always say landmarks, because there are some proxies in order to partition your space, your big metric space. Of course, here we are just talking about Euclidean space. Then we recurse and repeat according to each non-empty Pi. So we stop recursion once we reach depth I. And it has a very meaningful tree structure. So we go here, I said we sample T IID, so 1, 2, up to T. And then, so this is the first depth. You have the final depth, which is the case depth. And from here, you go again for all of the points in this. We go again, and then we sample T of them. Then we go again, and we sample T of them. So you see it has a nice tree structure. So the above procedure that I showed you generates a tree of depth K and degree at most T. So now to answer a query Q, we start at the root of that tree that I showed you and descend into the PIs, in the QIs, such that ZI and Q is greater than ZQ. And we eventually reach the case level. We iterate through all the points stored in the leaf. in searching for a neighbor. And the parameters tk, eta s, and eta q depends on cr, rho s, and rho q. So this is dependent on space. This is your query time exponent, and s is the space. So we have three regimes. The regimes, Ilya Razenshteyn uses the word regimes. So we have three regimes. You can say that the exponent, the eta s and eta q are equal. So you call it a balanced regime. Then the exponent are also equal. If eta s is less than eta q, space is less than query, then we have fast query. In this regime, we have fast queries. So it's a trade-off between space and time, between pre-processing and space. So in this regime, we have query is less than space. And the last regime is that your space is bigger than Q, and in this way you have a low memory regime. Low memory regime. And rho s is less than rho q. So in general, rho s and rho q for a data independent is this, and Ilya's approach has a better result. This is for Ilya in Microsoft. And for data independent partitions, so if pairwise distances between data points are distributed roughly like a random instance, we could apply data independent procedure. But if not, you can manipulate the data set in order to reduce it into a random looking case. Namely, we search for low diameter clusters that contain many data points. We extract these clusters and we enclose each of them in a ball of radius smaller than 1, and then we recurse on each cluster. So for points which do not lie in any cluster, we perform one step of data independent algorithm. I've talked about cut modulus and those things in previous lectures. So I just showed the Gaussian and tail bounds that f of rho, if rho is greater than 0, is defined by probability. Of course, Z is drawn from a d-dimensional normal distribution. The probability that this inner product, so of course U is in SD minus 1, is greater than rho. We want to look at this event. In probability, we should see which events are independent, which are mutually exclusive, and which are independent, and which one are dependent. So let's just do it. We define G. So F and G are very important. S, rho, and sigma. This is the probability that inner product is greater than rho, and Z and V, U and V are just 2 points. Okay, so the inner product as this is greater than sigma, and I should say that U and V are in SD minus 1. So you should imagine like this. You have U, you have V. You don't care about them. You care about the distance between them, and which is S. And if this is 1, and they have the angle between them is theta, then you can have beta s and alpha s the projection of that. So it's easy to see that sine is beta s, and this is 1 minus alpha 2s. This is sine of theta. And so I have defined G. So the value of G and rho and F does not depend on specific choice of U and V. And it depends only on the distance, as I said. So clearly, G is a non-increasing in S for fixed rho. This is rho and sigma. And F is a tail bound for Gaussian distribution, and G can be seen as a 2D generalization of F. So let me say a very interesting lemma that we need that. We need it. The lemma says for rho goes to infinity, f of rho that I have just defined is e to the minus 1 plus order of log rho over rho 2 over 2. So by the 2 stability property, you can write f of rho, the probability z is drawn from n, that the inner product of z and u greater than rho is equal to probability that x is greater than equal to rho, and this is 1 over 2 pi rho to infinity e to the minus x squared d of x. And this is e to the minus rho squared over square root of 2 pi is equal to 1 over square root of 2 pi rho to infinity 1 minus 3 divided by x to the 4th e to the x2 over 2 dx is less than equal to 1 over 2 pi rho to infinity x2 over 2 dx is less than 1 over 2 pi rho to infinity 1 plus x2 e to the minus x2 dx, and this is just 1 over 2 e to the minus rho squared over 2 pi. So this lemma is interesting, and our data structure is a rooted tree, as I said. So we sample t of them, as I said, 1, 2, 3, and in the next depth we have k depths. In the next depths we go sample again. We go and sample again t of them, and so our data structure is a rooted tree where each node corresponds to a spherical cap. The tree consists of k plus 1 level of nodes, and so each node has out degree at most t. For example, this, except root, of course, this one has a degree at most t. And so we will index levels by 1, 0 through k, where the host level consists of the root so each node up to the k minus 1th level has at most t children. So there are at most t to the k nodes at the kth level, and for every node v, for example, in this